If you're watching this video, you're probably like me when I first started NMR and you were doing the problems in the book and it wasn't making sense and you kept getting every single one of them wrong and you had to turn to YouTube to find help. But what really helped me understand is practicing and going through the book and learning all of the patterns that go with NMR. And after I learned the patterns, I started to understand things better. So in this video, I'm going to teach you all of the patterns that I learned from the book. And if you haven't started NMR, hopefully this will help you understand it before you start it, because it's definitely not something that can be easily understood the first time. So NMR, the first thing that you should consider when you are trying to dissect an NMR is look at the HDI, or the degrees of unsaturation. So the formula for HDI is 1/2 2C plus 2 plus nitrogen minus hydrogen minus any kind of like bromine, chlorine, halogens. So once you've gotten the HDI, and I'll go over how to solve HDI as I go through this video, but you should probably already know how to do it if you're on this part of the chapter. After you've done HDI, you should count the neighbors. Notice the signals. So when you're doing a NMR, how many signals there are is like how many hydrogen signals there are. So like I'm looking at the HNMR. So if you had something like this, let's say it was like there we go, something like this, you're going to have 1, 2, 3, and yeah, there will be 3 signals in here. And technically, these 2 hydrogens are one signal. These 2 hydrogens are one signal. And then this hydrogen is another signal. And it all depends on how far away it is from the group. This hydrogen is not its own. Actually, no. It is its own signal. Sorry. This is also a signal because it's connected to a carbon. So any hydrogen that's connected to a carbon that is different will count as a signal. Since these 2 hydrogens are relatively the same because they're the same length away from the carbonyl group, they're going to be one signal. So whenever you get an NMR, for that example, I think it was like 4 signals, you're going to get like 4 signals on your NMR. After you notice your signals, you should also notice integration. So when it comes to integration, there's 2 types that you can see. So usually when you're told to draw out an NMR, you're going to get the absolute integration, which just means that how much they put above the peak is how many hydrogens you actually have at that signal. You might also get a relative integration, which we'll see an example of relative integration later, which just means that like you might get a problem that says like, let's say the formula was like this, and you have a signal that says like it's an integration of 2. When you see this, that just means that there's some symmetry in the molecule. So 2 doesn't actually mean there's 2 hydrogens. You have to scale it up so that you can get 4. But usually when you get relative, you're given a multiple choice question. But for drawing NMRs, I've only ever seen absolute. The next thing you're going to know is you have to know the patterns, which is the biggest part to doing NMR. Like if you don't know the patterns, it's going to be really hard to understand NMR. And if you do know the patterns, you can do it in under like less than a minute when you're doing NMR, because you're just going to see stuff and you're like, oh, I know what that means. So you really need to memorize the patterns. Like it's a lot of stuff, but like it will help you so much more in the end. Okay. So another thing I want to go over is for HDI. if you have one HDI, like when we calculate it, if you have one HDI, that would either mean you have a ring or you have a pi bond. And so like either like could be like this, could be like this. And technically there can be triple bonds, but I've never seen a triple bond. But if you had a triple bond, that would mean you have 2 pi bonds. So technically you would have 2, that would take up 2 HDI. But I would not worry about triple bonds because I've not seen it. But just so you know, in case they throw something like that at you. Okay, let's move on with the patterns. So, I have a lot of the different kind of like things you need to look out for when you're calculating or you're trying to draw an NMR. So, these are the type of like groups that you can have on this side. And this is a chemical shift. So, I'm just going to list them all out for you. So, if you have a methyl, which you should probably already know this, but if you don't, a methyl is around 0.9, methylene is around 1.2, methane is around 1.7, allylic hydrogen is around 2, alkylyl is around 2.5, aromatic methyl is around 2.5, alkyl halide is around 2 to 4, alcohol is around 2 to 5. Phenylic hydrogen is 4.5 to 6.5. A hydrogen that's on a aromatic ring would be 6.5 to 8, which I would note this because you're going to see this a lot. Aldehyde, which you will also see this a lot, is going to be around 10. Carboxylic acid is around 12. So these 3 are kind of easier to remember for me because they're really high up. But yeah, I did see a lot of those. Some other patterns that you're going to see and you need to recognize is when you have like a ethyl, you're going to usually, well, you will always have something that looks like this. So, and this is in absolute. So if you have an ethyl, you'll have something that looks like this. So you have 3 peaks, which means that you have 2 neighbors. And why is it 2 neighbors? Because if you were to, I heard this from someone else on another YouTube video, but it really helped me understand. If you were to have, let's say, you were on a street. When you were trying to tell someone, someone asks, how many neighbors do you have? You don't include your family, but, instead, you, include the people around you. So, let's say that these were hydrogens. If I were to ask you, how many neighbors does this signal have? You're going to say it has 3 neighbors. So let's say that you had this carbon has 2 hydrogens, which would be this here. You would say that it has 3 neighbors because these are next to you. But you don't count your family when you're saying oh, how many neighbors do you have? You don't count your sister or your dad. You say oh, it's my neighbor, Jill, Bob, and Jan. They live in a house together or something like that. So that is what you would say. So when I say this peak has 4, a peak of 4 indicates that you have 3 neighbors. So for every peak, you're just going to be p minus 1, right? Because to find the neighbors, you need to subtract 1 from the peak. So this peak is 4, but it really means that you have 3 neighbors. This is a peak of 3, but it really means you have 2 neighbors. So, this here is the integration. So, you can think of that, if it's absolute, you can think of that as that's how many hydrogens you have. So this here would mean that you have a CH2 connected to 3 neighboring protons. So it could be like a CH2 to a CH3. And then this CH3 has 2 neighboring protons, and that's how you get the triplet peak here. So that's the first pattern you should notice is ethyls. So whenever you get an NMR and you see something that looks like this, you likely have an ethyl. The next one is isopropyl. So if you were to have an isopropyl, okay, it's a little bit wobbly, but you can kind of see though. If you were to have an isopropyl, you're going to have something that looks like this. So there's going to be a peak with 7, which would mean that you have 6 neighbors, and it has an integration of 1. So let's draw that out. So you have an integration of 1 connected to 6 hydrogens. It has 6 proton neighbors. But how can that be? Because the most you can have is like with the methyl, which would have 3 protons. Well, that's where this comes in hand too. Because if you realize, or if you can see, really what you're looking at is there's a split. So in isopropyl, if you know what it looks like this, you're going to have these 2 methyl groups are going to be the same. Like they're going to have the same signal. These are hydrogens here. And then there will be another signal that's right here. So this signal, the CH, is going to have a neighboring of 6, which is what is here. These methyls are going to have a neighboring of 1, which is here. So that's how an isopropyl would look. So if you see something that has a heptet with a signal or integration of 1, and then you have a doublet with an integration of 6, that would indicate that you have an isopropyl. Next pattern you can see is a tert-butyl. So tert-butyl will be a singlet with an integration of 9. So let me explain this, because this might be kind of confusing, because you would think like there would not just be one signal. But if you notice, this carbon here has no rooms for hydrogen, so therefore it has no signal. But these signals here are all the same, and there happens to be 9 hydrogens here, but they have no neighbor. So if you have no neighbor, that means that you're a singlet. You only have 1 peak. Now we're going to get into like the aromatic ring. So remember when I told you that seeing a signal of 6.5 to 8 is really important and you should memorize that chemical shift? Well, that's what I'm talking about here, because there are a lot of patterns that go with aromatic rings. So, for example, a symmetrical aromatic ring that will have a chemical shift that looks something like this. Yeah, it'll have a singlet with an integration of 4, and it'll be somewhere around 7. So like, let's say you had this compound here. It's an aromatic ring, and there's 2 methyls on the side. Okay, so if you notice, these 4 protons here, there's a hydrogen on each carbon. They all have the same signal because there's symmetry here. So since they all have the same signal and they all have a integration, since they all have the same signal, and they only have one neighbor, it's going to be singlet, and there's 4 hydrogens in that signal. So as for these 2 methyl groups, they're also the same signal, so you're only going to get one other peak. And an aromatic ring with a methyl group on it shows up around 2.5, so we'll just put like 2.5, and this will show up as a singlet with an integration of 6. So the NMR would kind of look like that. The next aromatic ring to look out for would be an asymmetrical aromatic ring. Okay. So when you have an asymmetrical aromatic ring, you're going to have 2 doublets with an integration of 2, again, around 7. And why is this? Because let's say, like, for example, this, I'll draw it kind of similar to the one that we just did. So you've got a CH2, you got an ethyl on this side, and you've got a methyl on this side. So now this is not symmetrical, like this is not the same. These sides are not the same. So these 2 protons here, they're the same. And then I'll make this a different color. These 2 protons here, they are the same. But they are not the same like to each other. Because this has a different chemical shift due to this. This has a different chemical shift due to this. So you're going to get 2 peaks around 7. They're going to be very close to each other, but they're still two different doublets, right? And why are they doublets? Because this has a neighbor here, so it's a doublet. This has a neighbor here. Okay. And also, you know what? I just realized something about this problem up here. I think I said that these have a neighbor here. That's not true, actually, because it's a singlet. It has no neighbor. So, sorry for saying that. I actually mean these are all the same signals, so they would not have neighbors because, again, like I said, they're in the same family. You don't count your family as neighbors. So, yeah, they actually have no neighbors because there's no proton here. So that's why it ends up as a singlet like that. So sorry for that if I made you confused. I somehow forgot about my own saying, but it's okay. Okay, so like I said, it's a doublet because you have a neighbor here, this one has a neighbor here, and there's 2 signals, 2 hydrogens, so you're going to get 2 doublets here. So for example, this one is going to have some more signals here, and it would probably show up, one would show up here, do this, show up something like this, and integration of 3, and this and this. This one has 3 neighbors, so it would be like 4, 3. Oh, okay. You know what? That's 3. So it would look something like that on an NMR. But like I said, really the important thing is that you're noticing that there's 2 doublets with an integration of 2, and it has to specifically be an integration of 2. And if you see that, then you know that there's an asymmetrical aromatic ring, specifically a 1,4 asymmetrical aromatic ring. Okay, so like I said, this is only for 1,4, but there are others, like there's 1,3, and there's 1,2, but these are kind of harder to really identify, but I'll tell you like how to identify them. So if you see a problem and you don't see these kind of like identification cues, you know that it's not going to be 1,3 and it's not going to be 1,2. So it'd have to be 1,4, or it would have to be like an aromatic ring with just one group coming off of it. But like I said, this one is harder to understand. So if you have a asymmetrical 1,3 aromatic ring, first of all, you're going to have 4 peaks. You're going to have 2 doublets of doublets, and you're going to have 2 triplets of doublets, or doublet of a doublet of doublet, which this is why I said it's kind of harder to like identify this or like understand it, because when you get into like multiplexes like this, doublet of doublet of doublet, it's really hard to like see that when you're looking at a problem. Like it'll look something like, I don't know, it'll just look like this. Like it's just, you like can't really read that. Like it's kind of hard. So really what you should just notice is that if you see like an asymmetrical aromatic ring, or no, if you see an NMR and around 7, there's like 4 different peaks, and they're all going to be like some weird like multiplex, but if there's like 4 different peaks, it could mean that you have a 1,3. And it's the same for 1,2. Like 1,2 has 4 peaks as well, and you're going to see 2 doublets of doublets, or 2 triplets of doublets, or doublets of doublets of doublets. And by the way, if you're wondering what like a doublet of a doublet of a doublet even looks like, I can try to draw it out for you, but like I said, it's kind of hard to see that on an NMR. It would look like this. I don't even know. Doublet. This is doublet, doublet, and a doublet, and a doublet. Yeah, it's just weird. It just looks like a weird mess. But like I said, 1,3 and 1,2, all I would really say is check to see if there's 4 peaks. That could indicate that you have a 1,3 or a 1,2. Okay. Now, I have some problems that I'm going to go over. Okay, so let's start this off like kind of going how I said, where we're going to start by calculating the HDI. So if you forgot the formula, I'll write it down again. So it's 1/2 of 2 carbons plus 2 plus nitrogens minus hydrogens minus any halogens you have. So, well, I don't have a calculator, so I think I can just do it in my head anyways. But, so let's do this. So, let's plug it in. So 2 times 9 plus 2 plus, there's no nitrogen, so we're not going to add that. So actually it's going to be minus our hydrogens. And there's no halogens, so we're just going to ignore that as well. All of that times 1/2. So 2 times 9 is 18, plus 2 is 20, minus 12 is 8, divided by 2 is 4. So the HDI for this problem is 4. So let's just keep that up here. And I'll erase this so that there's more room. Okay. Next thing is, if you've noticed by now, good job, because here is a aromatic ring. There is a signal at 7, so that means that there's likely an aromatic ring. So let's just start off by drawing that in. And already, if you've noticed, there's 1, 2, 3, and a ring. So 3 pi bonds and a ring is an HDI of 4. So we've already completed our HDI. But the next thing I want you to notice is that both of these signals are singlets. So they have no neighbors, but this one has 3 hydrogens, this one has 9 hydrogens. So the only way this could really go, since this isn't a 1,3, it's not a 1,2, and it's not a 1,4 aromatic ring, because you would see different kinds of signals here, is I would say you could put 3 methyls here, and that would leave room for some hydrogens here. All 3 of these hydrogens have no neighbors, so that would check off this. And these hydrogens all around here, there's 9, and they also have no neighbors because there's no neighbors on this carbon, but they're all the same signal because it's symmetrical. Oop. So that would make for 9, which would check this off. So for this problem, it's an aromatic ring with 3 methyls. Okay, for this next problem, this is a little bit harder, but I think it's still doable. First thing we're going to do is calculate the HCI. So it's going to be 8 times 2 plus 2 minus the hydrogens. And if you're wondering about oxygen, you do not add this to your HCI formula. Oxygen does nothing. So carbons times 2 is 16, plus 2 is 18, minus 10 is 8. And then divided by 2 or times 1/2 is the same thing, equals 4. So for this problem, there's an HDI of 4. Okay, next thing that we're going to do is we're going to look at our signals. So I already see some patterns here. Right here, again, there's an aromatic ring. And specifically, if you remember, it's 1,4. And also, if you want to pause this before I actually start solving it, you can do that too. But I know I'm kind of just going to the next problem. I'm not really pausing. But if you want, pause the video and try this for yourself. So already I noticed that we have a 1,4 aromatic ring, but we don't know it's here yet. We don't know it's here yet. So let's not assume this is a methyl. This is not a methyl. It's just showing that there's some kind of bond going on there. Okay, so since we know what this is, next thing that we're going to notice is we have a ethyl. Because right here, this is the pattern of an ethyl. So we've got CH2 connected to 3 protons, and we've also got a CH3 connected to 2 protons. So that's an ethyl. So I think the next thing that we have is we've got one single hydrogen here. So I think I'm going to start putting this together because I'm pretty sure this ethyl would have to go here because where else would it go? We only have one more hydrogen for one more group. So you know that the ethyl is going to go on the edge here. And now we've used 1, 2, 3, 4, 5, 6, 7, 8 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So all we have left is 1 hydrogen, 1 oxygen, which that would give us a alcohol. So the end of this is an alcohol. So this compound would look like this. Okay, the next one. Okay, so this one is a little bit harder. So if you don't understand it at first, that's okay, because when I first saw this, I didn't really understand it at first either. I kept getting it wrong until I finally understood how to piece this together. And another thing is, if you're alarmed by these like S-shaped looking things, it's just saying that there's an integration. When you're calculating integration, usually like if you're in like an orgo class, you're just given the integration number. But I know like there's a way to calculate integration, and it's like something about like the area under this. So that's all that is, but don't worry about it. It really means nothing. It's just saying there's an integration, and the integration here is like 6, for example. Okay, so this one is an example of one you have to kind of pay attention to. Count how many like atoms you've used, and just pay attention to like all the little details. So the first thing that we're going to do is we're going to calculate the HCI. So to calculate the HCI for this problem, first we're going to add in our carbons. So 8 times 2 plus 2 minus 15 for our hydrogens minus 1 for our chlorine divided by 2. So 8 times 2 is 16, 17, 18. And then minus 15 is 3, minus 1 is 2. 2 divided by 2 is 1. So the HDI is 1. Okay, so let's just keep that up here. The next thing that we're going to look at is our integration. Do we have any patterns? And let's see. So I'm not seeing any clear patterns right now, but I am seeing there could be like two symmetrical ethyls, because we do have a 4 and we've got a 6 like this. So that could indicate symmetrical ethyls, because if you were to have something like this, these are the hydrogens, and they're symmetrical, you would have 4 and 6. So that could be 2 symmetrical ethyls. So we'll just keep that on the side. Like, I'm going to write it in a different color than what I'm going to write my answer in, because we don't know yet if that's actually true or not. So CH2, CH2 to CH3, CH3. Okay, so something like that. I don't see any other clear patterns, so we're just going to kind of look at what we've got. So here we do have a CH that could be connected to a CH2 because it needs 2 neighbors. And it could be something like this as well, but it's less likely. So it is less likely, so I'm just gonna assume that it's like something like this. Because if you think about it, how I think about it is like, if you have something that looks like this, you're gonna have to have like a lot of like things coming off of it that like won't add protons, which that just like doesn't really make sense, you know? So we're gonna say it's like this. So that's what I think this is. This here is a CH2 connected to CH2. And again, the same reason, I don't think it's going to be something like this, because that wouldn't make as much sense. Sometimes it is, but usually I write it like this first before I start thinking it's going to be something like that. So we're going to say it's that. And then this here is a multiplex. If you can't tell, I mean, I know like my spikes aren't very good, but this is supposed to be unreadable. These you're supposed to be able to read. This is unreadable. It's a multiplex. So what that means is that there's 2 different numbers of protons on either side. So that would kind of make sense if we were to like, these could go together and that could give a multiplex. So we're going to put that together. So CH2, CH2. So let me write this better, actually. So if you remember, I said this is going to be a CH, and I think it's going to be attached to a CH2. Just like how I said, I think these are ethyls, but I'm not sure. I think this is a CH2, but I'm not sure yet. And then this, I think, is a CH2, and I think it's attached to another CH2. So that's what I mean when I say, like, add. So now we're going to add these two, like, I guess, things that I think are true, and we're going to get this, which matches. So this must be what it is. And then after we've got that, let's just quickly take a moment to, like, count how many carbons do we have left, how many hydrogens do we have left. So we've used 1, 2, 3 carbons, so we've still got 5 carbons left. 1, 2, 3, 4, 5. We've used 5 hydrogens, we've got that many left, and then we've still got all of our, like, halogens and our oxygens. So the next thing that I'm going to say is this CH, it has to be attached to 2 other, like, atoms that don't bear any protons. So what could that be? Well, we do have some oxygens, and oxygens don't have to bear protons. Like, there could be alcohols, but that wouldn't be a thing. Like, you don't ever see something looking like that. So I think that's going to be our next step. So let me just write it like this so it looks a bit cleaner. And for this to be a CH, there has to be 2 other bonds. Let's see. We've still got this, like, proposed ethyl groups, which I think these are ethyls, because if you notice, if we used 2 oxygens like this, we're going to go down to this. We still got our chlorine, so we need to figure out what to do with that. But if we were to add ethyls, CH2, CH3, CH2, CH3, we've now used all of our hydrogens, and we have 1 more carbon left. So, this should be, there's only 1 here. So it should be like that. So what does that leave room for? Well, it didn't show up on here, but we still know what it is because there's only one place this could go, and that would be on this end here. So, and also if you notice, it says that we have a strong absorption at 1800, which means that there has to be some kind of carbonyl group. And with that, I think the final proposed molecule is going to look something like this. This is starting to get kind of messy. You know what? I'm not even going to draw that. I'm just going to put it on here. I think it's going to look like this. So this would be the final molecule here. And if you check, does have the correct HCI. So it's always important to check when you're done with your problems that does it have the correct HCI or no. And it does. There's only 1 pi bond here and no rings. Next problem, we're going to start getting into, like, some harder problems, but these problems, I made them into, like, a multiple choice because I think it's also important that you see the patterns whenever you're doing multiple choice, because some of the patterns are harder to see, and if you understand the patterns, like, and you can do the multiple choice quickly, you have more choice or more time when you get to the free response. So, already, if you remember, I'm seeing 2 patterns here. And also notice, there's no formula here, so we can't even calculate the HCI or anything like that. And there's also no integration values, so we're not going to draw it out. But what I do know is that 10 is an aldehyde, and something at 7, specifically, there's a 1,4 aromatic group. I forgot the word for a second there, but yeah. So we've got an aldehyde and we've got a 1,4 aromatic. So already, this is not 1,4. This has no aldehyde. This has no aldehyde. This is 1,4 and it has an aldehyde. So this would be our answer here. Okay. The next one, remember when I was saying that for multiple choice, you might get some problems that don't show you the absolute integration, but they give you relative? Well, this is an example of one of those problems. So it won't tell you that you have a relative, like, integration. It'll look something like this. Like, there's no indication, right? Like, there's nothing saying that. But as we walk through this problem, I'll explain to you why, like, I figured out this is a relative integration. So let's first look at what kind of patterns we've got. So I don't see any clear patterns, but let's draw out what this would look like here. What would these three look like? So first of all, we've got 1, 2, 3, 4 peaks. That would mean that it has 3 neighbors. So it's a CH2 with CH3. And again, it could be CH2 CH. That's another like option, but we really have to like check our other parts of the problem first. So let's just put both of them down just for fun. But this is really what I think it is, though, because I'm seeing now that there does seem to be like an ethyl pattern here. So I think it is an ethyl. But let's just draw it out. So we've also got a triplet with an integration of 3. So it's going to be a CH3, CH2. So that just eliminates this. It's not going to be this because this is a clear ethyl. So if you saw that pattern when we first looked at this problem, when I didn't notice it, good job, because like I said, even though I know the patterns, sometimes like it'll slide past you and you don't notice it at first. But as you do the problem though, if you know the patterns, you're going to like notice like, oh, I missed this when I first looked over it, but now I know what it is. And it'll help you eliminate like answers that, like I said, like where I was like, it could be something like this, but I know it's not that because it's an ethyl pattern. Okay, so we've got a clear ethyl, and we also have a peak of 1, which is really strange because if you look at these, I don't see any, like, anywhere that just has a singlet that also has 1 hydrogen on it. So that's when looking at this from like a relative integration kind of helps, because we do know that we have an ethyl, right? So already we know that it has to have an ethyl in it, but we also know that since there's no like CH in any of these problems, this is likely relative, which means that it's fully symmetrical. So when the integration was taken down, they just kind of like simplified it. So really, this is a 4. This would be 2 hydrogens. So there's 4 hydrogens, 2 hydrogens, and there's 6 hydrogens here. But since it was symmetrical, they just simplified everything. So the only one here that's symmetrical that also has an ethyl is this one, which you can see here, CH3, CH3, that would get you 6, CH2, CH2, that would get you 4. Here, there's a symmetrical, like, this is like the line of symmetry, but this is going to be a CH2. So always remember that sometimes they won't tell you, but they can show you a problem that you need to look at it from like a relative integration perspective. Okay. This is the last problem. First of all, we do have like the formula here, so we can calculate the HCI, but I think all that would really do is like eliminate this one. but like just for practice, I guess we could. So we've got 10 times 2 plus 2 minus 12 divided by 2. So 10 times 2 is 20 plus 2 is 22 minus 12 is 10 divided by 2 equals 5. So we know that the HCI is 5. So already this cannot be it because this only has an HCI of 4. It has to be one of these here. The second thing I've noticed is if you know your IR spectrum, this here is showing that there's a ketone, but it's conjugated, which makes it have like a lower value. So it has a lower wavelength. And so it needs to be a conjugated ketone. It is probably a conjugated ketone. So this here, not it. This here, not it, because it's way too far. Especially this one's way too far. This one is like far. So, it's not as far as this one is, but it's still pretty bad. So now we're down to these two. But, if you notice, this is not an aromatic compound. So this doesn't even have an HCI of 5. It doesn't even have an HCI of 4. It has an HCI of 2. Because you've got a ring and you've got a pi bond, but you need more than that. So it's not going to be this. So this is likely this here. Well, it is your answer because we just proved how like all these cannot be the answer because these two would not match the IR. This doesn't have a high enough HCI. This has a really low HCI, not even close. So I hope that helped you understand. I know there was like some parts where I kept going back and forth, but this is just like a hard topic to understand. It's a hard topic to explain. But in the end, I'm really going to say the best way to get good at NMR is, like I said, learn the patterns, and you also need to practice a lot. Like, I mean like a lot. Like when I did this, I went through the practice problems in the books like at least twice, and then the third